everyone, Glory Valentino Moore is my name from the Department of Metallurgy and Structural Integrity at the Center for Research in Advanced Material Science (CIMA). Organizers of this conference did a very good job. Thank you very much. Presently, thin films are among the most active research field in material science because of their technological application. I am presenting the synthesis and characterization of polycrystalline bismuth manganese oxide and copper-doped bismuth manganese oxide thin films. So let's get started. In the course of this presentation, we'll see the introduction, objectives, materials and method, material characterization, results and discussion, finally conclusion. Introduction. Bismuth manganese oxide has found application in a wide variety of fields owing to its fascinating multiferroid properties. If we see here in figure 1a shows the relationship between the multiferroid and magnetoelectric material. When we talk about the multiferroid, it possesses two or more ferroid order like the ferromagnetic and ferroelectricity or ferroelasticity occurring in the same phase. And talking about the magnetoelectric, it must possess magnetic and electric order coupled as a ferromagnetism with a Curie temperature of 105 to 110 Kelvin. It has a magnetic moment of 3.77 volts moment on each manganese 3 plus ion. Though bismuth manganese has been always synthesized at high pressure and temperature. Here we have the structure of bismuth manganese oxide and the copper-doped bismuth manganese oxide. These two figures were stimulated using phase star. This figure shows a perovskite-like structure which crystallizes as a non-central symmetry space group of C2. The bismuth atoms are located in the lattice body. Manganese atoms are located at the lattice vertex position, and there are two inequality bismuth sites. The first bismuth site is bonded in a 4-coordinate geometry to 4 oxygen atoms, while the second site is bonded in a 6-coordinate geometry to 6 oxygen atoms. Manganese sites exist. The first and second are bonded to 6 oxygen atoms, and oxygen are bonded on bismuth and manganese atom bond all around them. The multiferroid behavior of bismuth manganese oxide is typically attributed to the existence of two dissimilar lattices. Two structural effects in these materials are inversion symmetry breaking, which give rise to ferroelectricity, manganese atom base sublattice, which is responsible for magnetism. Here shows the crystal structure of the copper-doped bismuth manganese oxide. The copper here is bonded in a distorted square coplanar geometry to 4 oxygen atoms. The objectives are growth of bismuth manganese thin film using radio frequency magnet transport ring on platinum substrate. Structural characterization of bismuth manganese on platinum substrate by X-ray diffraction. Finally, study the morphology thickness of bismuth manganese oxide thin films by means of energy dispersive spectroscopy, and also the composition of the thin film of bismuth manganese oxide on platinum substrate by scanning electron microscopy. Here is the experimental details of the copper-doped bismuth manganese oxide thin films. These were the parameters used for both thin film, but the thicknesses of bismuth manganese oxide was 60 nanometer, and for copper doped bismuth manganese oxide was 70, but all parameters remain the same. We have the target here of bismuth manganese oxide and also the copper target being deposited on platinum substrate. Material characterization, we have the X-ray diffraction, scanning electron microscopy, and energy dispersive X-ray spectroscopy. Pure bismuth manganese oxide, we have it to be 58 nanometers, and the thickness for the copper doped bismuth manganese oxide, we have it to be 68.6 nanometers. Here is the X-ray diffraction pattern of the pure bismuth manganese oxide. This is the theoretical bismuth manganese oxide, which was also simulated to match with the pure bismuth. And here is the copper doped bismuth manganese oxide. The marching here was done using a PDF card of mono C2 space group manganese oxide from the theoretical here. And from here, we can see that the peaks for the copper doped bismuth manganese oxide appear to be more intense than that of the bismuth manganese oxide. And here we have several peaks signifying that is a polycrystalline thin films. In our calculation also for the crystalline side, we saw that the copper doped bismuth manganese oxide, the crystallinity decreases than that of the pure bismuth manganese oxide. The copper doping may act as an impurity at higher doping concentration because the existence of impurities decrease the lattice parameters and decrease the crystallinity, thereby causing decrease in crystalline size like we got for the copper doped bismuth manganese oxide. Because the elemental composition of bismuth manganese oxide in 3A here we see the bismuth manganese oxide spectrum with their respective elements here. In C, we see the EDA spectrum of copper doped bismuth manganese oxide with its respective elements here. But the thin films are in order and homogeneous. Conclusions: pure bismuth manganese and copper bismuth manganese films with smooth surface morphology and perovskite structure were deposited on platinum substrate by radiofrequency magnetron sputtering technique. The X-ray diffraction pattern shows that both films are crystalline in nature. The intensity of copper doped bismuth manganese oxide peak increase with the increase in the thickness. Thickness of bismuth manganese oxide and copper doped bismuth manganese oxide film were 60 and 70 nanometers respectively. Finally, the crystalline size decreased with the doping of copper, which may be due to the decrease in the ionic radals of copper. Thank you for your attention. The authors profoundly thank and acknowledge CONACYT and the members of staff at the Center for Research in Advanced Material Science, CMAV. I'm open to your questions.